Welcome back to the deep dive. This is where we really get into the weeds, pull apart the key ideas from cutting-edge research and hopefully give you those aha moments without you having to wade through everything yourself. Today we're tackling something I find really fascinating. It's a piece of research that, honestly, could change how we think about robot intelligence, especially adaptability. So picture this, a robot learning to walk. But it's not just about getting from A to B, it's about doing it smoothly, efficiently, gracefully almost, and crucially, being able to adapt instantly, like on the fly, if something unexpected happens. Say, one of its legs suddenly stops working right, or the ground suddenly tilts uphill.
Exactly. That's the kind of real-world challenge that standard approaches often struggle with.
And that's precisely what this paper, Meta-Reinforcement Learning with Minimum Attention, gets into. So our mission today for this deep dive is to really unpack how this principle, this minimum attention, is changing how AI agents learn. The promise here is pretty big, making them not just learn faster, but also become way more adaptable, more stable, and interestingly, even more energy efficient, especially in environments that are, constantly changing and unpredictable.
Right.
We're going to try and peel back the technical layers here, look closely at the mechanics in the paper, explore the results they got, which are pretty impressive, and figure out what makes this approach different from other, state-of-the-art AI methods. And just to be clear for everyone listening, we'll be keeping our focus squarely on the technical innovations and what they mean in practice.
Yeah, and what I find particularly captivating here is how they've blended different insights. It takes inspiration from, well, biological control systems. Think about how animals, or even us, learn to move. It's incredibly smooth, coordinated, efficient, right?
Yeah. Effortless, almost, once learned.
Exactly. And they've managed to translate that kind of natural fluidity into a really powerful regularization technique for AI. So we'll be digging into the empirical evidence they present, which really demonstrates some clear advantages, especially in these high-dimensional, complex, dynamic environments, the kind you always encounter with real robots. Our focus, like you said, is purely on the technical side, the breakthroughs, the performance, the stability implications.
Okay, so before we jump right into minimum attention, let's maybe set the scene a bit. Talk about reinforcement learning, RL. Because, over the last, 10 years, RL has just exploded.
Oh, absolutely.
We've seen AI master tasks that seemed impossible before. Games, complex robotic control. I think a lot of listeners will remember those big moments, maybe around 2015, when deep RL systems started showing up playing video games at human level.
Yeah.
That felt like a huge leap.
It really was a watershed moment, an incredible journey to watch unfold. But, despite all the successes, RL hasn't been without its challenges. It's not always a smooth ride. Broadly speaking, we tend to categorize RL into two main camps: model-free and model-based.
Right.
Model-free methods. Well, they're kind of like learning purely through trial and error, lots and lots of it. They learn directly from experience, right? From seeing what happens when they take an action in a certain state.
Yeah.
But they don't build an explicit internal map or model of how the environment actually works. Now, they can get really, really good eventually, achieve high asymptotic performance, as we say. But, this is a big but, they often need a huge amount of interaction with the environment, like millions or even billions of steps, and tons of learning time to get there.
So it's like learning to ride a bike just by falling off thousands of times until you eventually figure it out without ever really understanding the physics of balance.
That's a pretty good analogy, yeah. Brute force learning, in a way.
Okay, so if that's model-free, then model-based must be like having that physics textbook.
Yeah.
Or maybe like having a simulation in your head you can practice in.
Precisely. Model-based RL tries to explicitly learn a model of the environment's dynamics. It tries to predict, okay, if I'm in this state and I do this action, what state will I end up in next? Or what reward will I get?
Right.
And the big promise there is sample efficiency. It needs way less real-world interaction data to learn effectively.
Which is huge, especially for things like robotics.
Right.
Where getting real-world data is slow, expensive, maybe even dangerous.
Exactly. It's a massive advantage in those domains, but there's a catch.
Always a catch.
Yeah. The big challenge for model-based RL is something called model bias. If the internal model the agent learns isn't perfectly accurate, and let's face it, in complex real-world situations, it almost never is, then the agent might find a brilliant strategy that works perfectly in its flawed internal model. But when you deploy that strategy in the real world, where the dynamics are slightly different, it performs poorly, sometimes much worse than a model-free agent would eventually reach.
So it thinks it's playing chess perfectly, but its understanding of how the knight moves is just slightly off. and it keeps making mistakes because of that.
That's a perfect way to put it. It's optimizing for the wrong reality, essentially.
Okay, and this is where the paper starts getting really interesting, right? They talk about the uncertainties that cause these problems.
Exactly. They highlight two main types of uncertainty, especially in model-based RL. First, there's uncertainty about the model itself. You don't know the true environment dynamics beforehand, and the model you're learning is constantly changing and hopefully improving as you get more data. So that directly feeds into the model bias problem.
Right, the map is constantly being redrawn.
Precisely. And second, there's the inherent stochasticity. Real environments are noisy, unpredictable. There's randomness in sensor readings and how actions affect the world.
Yeah, friction isn't always the same. Things wobble.
Exactly. So the agent has to deal with both the uncertainty in its own understanding and the inherent unpredictability of the world.
So given those challenges, how do researchers typically try to make agents more robust, more flexible, better at handling different tasks?
Well, two main strategies have really gained traction to deal with these uncertainties and improve flexibility. One is using model ensembles.
Okay.
Instead of learning just one model of the world, you learn several different models simultaneously, an ensemble. Then, when you need to make a prediction, you consult the whole ensemble. It gives you a more robust estimate, kind of averages out the errors or biases of any single model.
Like asking a panel of experts instead of just one gives you a better range of possibilities.
Exactly like that. It provides a better sense of the uncertainty in the predictions. Work by folks like Clavera and Kuretak in 2018 really explored this well. The second big strategy is meta-learning.
Learning to learn. Heard that phrase a lot.
Yeah, that's the one. The goal isn't just to teach the agent one specific skill really well. It's about teaching it how to learn new skills quickly.
Right.
Specifically, how to adapt to a new, unseen task using only a tiny amount of new data, what we call few-shot learning.
So it's like teaching someone how to learn languages fast, not just teaching them French.
Perfect analogy. It aims to bake in adaptability at a fundamental level. Think of Finn's work on MMML in 2017 that really pushed this idea forward.
So model ensembles give you robustness by combining viewpoints, and meta-learning gives you rapid adaptation by teaching the learning process itself.
You've got it. And both have shown really promising results in making RL agents better. But the real kicker in this paper, the core innovation, is how it cleverly combines these two ideas, model ensembles and meta-learning, and then adds this unique, powerful ingredient, minimum attention.
Right, that's the secret sauce we need to unpack.
Exactly. It's this extra layer that provides a kind of sophisticated regularization, aiming for even better stability and efficiency.
Okay, let's zero in on this minimum attention. It sounds, well, almost mindful, doesn't it? But what is it, technically speaking? Where does the idea come from?
Technically, it's an application of something called the least action principle.
Okay, that sounds familiar.
Yeah,
Physics, right?
exactly. It's a really fundamental concept in classical mechanics. Think about how light travels or how planets orbit nature often finds the path that minimizes a certain quantity, like energy used over time, or just action.
Huh.
In the context of control systems, which is what we're talking about with robots, minimum attention translates this into minimizing the changes in the control actions, changes with respect to both the state of the system and over time. The idea was formally proposed in this context by Roger Brockett, a really influential control theorist back in 1997, so it has deep theoretical roots.
Okay, minimizing changes in control.
Yeah.
Why is that so important? What's the benefit for an AI agent trying to, say, walk or manipulate something?
It's powerful because it acts as a very specific, and it turns out, very effective form of regularization on the agent's control policy.
Regularization, like a penalty to guide the learning.
Precisely. Think of it as adding a kind of smoothing penalty to the agent's decision-making. The paper defines it mathematically, JU, but we don't need to get lost in the integral calculus.
Shoo. Okay.
The key thing is it has two main parts that penalize two different kinds of undesirable control behavior. The first part, written as u squared, penalizes how much the control action u changes when the state x changes. This is often called the feedback norm or the Jacobian of the policy. Basically, it measures sensitivity. If the robot senses a tiny change in the world, the floor angle shifts a fraction of a degree, a sensor reading flickers how much does its motor command change in response.
Okay.
Minimum attention penalizes large responses to small changes. It encourages the policy to be less jumpy, less reactive to minor state fluctuations.
Got it. Don't overreact.
Yeah.
What's the second part?
The second part, AS squared, penalizes how rapidly the control action U changes over time, too. This is the feed-forward norm, or maybe more intuitively, the jerk. Like in physics, jerk is the rate of change of acceleration.
Right, how smooth the motion is.
Exactly. This term penalizes abrupt, jerky movements, slamming on the brakes versus easing them gently, making sharp, sudden turns versus smooth ones. It promotes fluidity and continuity in the agent's actions over time.
So putting it together, the math is basically saying, don't overreact to small changes in what you sense, low Jacobian norm. AD, don't make sudden jerky movements, low jerk norm.
You've nailed it. That's the essence. It's building in a preference for smooth, stable, less aggressive control.
Which sounds a lot like how biological systems work, right? Like human motor control. We're usually pretty smooth and efficient when we move, especially for skilled tasks.
Absolutely. That's a key inspiration mentioned in the paper. Think about skilled athletes, dancers, even just how we walk. There's an inherent efficiency and smoothness. This regularization explicitly guides the AI towards that kind of dexterous, safe, and fluid behavior.
Makes sense.
And interestingly, similar mathematical ideas have popped up in totally different fields, like controlling fluid flow. It suggests this principle of minimizing change or effort has really broad applicability for optimizing complex dynamic systems.
So it's not just for robots. That's fascinating. It sounds like this minimum attention thing is doing two key jobs at once then.
Yes, precisely. The empirical results show two major benefits. First, it leads to significant stabilization and reduction in variance during the learning process itself.
So the training is less bumpy,
Hmm.
less likely to go off the rails.
Exactly, which is critical for safety, especially if you're training in the real world or in applications where erratic behavior is dangerous. Stable learning means more reliable progress.
Okay, that's huge. What's the second benefit?
Second, particularly relevant for the meta-learning aspect, it enhances the few sampling capability. The agent can adapt much faster to new tasks using less data.
So it becomes a quicker, more efficient learner overall.
Yes, it learns faster, adapts faster, and it's more stable while doing it. It's like getting the best of both worlds, speed and stability.
Okay, this sounds really powerful.
Hmm?
But how do they actually implement this? How do you take this mathematical idea, this JU penalty, and bake it into the complex machinery of deep RL and meta learning? What does that architecture look like?
Okay, let's get into the technical blueprint. The algorithm they propose is a smart combination of existing techniques plus their minimum attention twist. It basically merges ensemble-based model learning with gradient-based meta-policy learning. And these two parts run alternately, refining each other over time.
Ensemble models and meta learning, like we discussed before.
Right. And it's designed for what's called a first-order nonlinear system, which sounds complicated, but it's actually a standard way to model many real-world control problems. First order just means the next state depends only on the current state in action. Nonlinear means the relationships aren't simple, straight lines, think complex joint movements. And crucially, they assume stochasticity.
The randomness, the noise.
Exactly. The system has to cope with that inherent unpredictability.
So not a perfect simulation,
Yeah.
but something closer to the messy real world.
Precisely. Now, the core innovation, the absolute key, is how they modify the reward function. In standard RL, the agent just wants to maximize the task reward, run faster, balance longer, whatever it is.
Right, get the highest score.
Here they define a regularized reward. Let's call it reg. And it's the original reward minus a penalty term based on minimum attention. So reg, R at times, plus ER. That is just a weighting factor controlling how much importance you give to the minimum attention penalty.
Whoa, okay, so the agent isn't just trying to get the reward anymore. It's trying to get the reward while also actively avoiding being too sensitive, low Jacobian, and too jerky.
You like it. It's optimizing a dual objective. Perform the task while and do it smoothly and efficiently. It creates this explicit trade-off.
That's really clever. So how does the learning actually happen with this modified reward?
Well, the control action U is typically determined by a neural network, right? A policy network. In this case, it's a standard multi-layer perceptron, an MLP.
Okay.
And the whole learning process cycles through two main steps, iteratively. It's conceptually similar to MML, model agnostic meta learning. You adapt models, then you update the meta policy. Step one is the model learning phase.
Right.
Here, they train an ensemble of models, not just one. The paper mentions using 7 networks and then picking the best 5, the elite models. These models learn to predict the environment's dynamics based on real interaction data. So, given state as and action A, predict the next state's prime. They minimize the difference between their predictions and what actually happens.
So the ensemble gives a more robust picture of the world dynamics, reducing that model bias problem.
Exactly. Collective wisdom. Then comes step 2, the meta-policy learning phase. For each of those elite models in the ensemble, they simulate trajectories, like the agent does mental practice inside each model's version of the world.
Okay.
Based on these simulations, they calculate a provisional policy update using something like vanilla policy gradient. This adapts the policy specifically to that model's dynamics. Then, and this is the crucial meta-learning step, they perform a final meta-policy update. This update integrates the information, the gradients, the returns gathered from adapting the policy across all the elite models in the ensemble.
Ah, so it learns from all those slightly different mental practice sessions.
Right. And importantly, for this final meta update, they often use a more stable optimizer like Trust Region Policy Optimization, TRPO.
TRPO. Why is that important?
TRPO helps prevent the policy updates from being too large or erratic. It keeps the changes within a trust region where the models are likely still accurate. This avoids situations where one bad update could destabilize the whole learning process. It ensures smoother, more reliable convergence for the overall meta policy.
So let me try to summarize my understanding. You train a team of mini-expert models on real data. Then you let the policy adapt to each mini-expert's view of the world, doing simulated practice. And finally, you combine all that adapted wisdom into one super policy.
That's a great way to picture it.
And crucially, because the reward function itself includes the minimum attention penalty, that wisdom they're all learning is inherently biased towards being smooth and non-reactive from the get-go.
Precisely. Minimum attention isn't just tacked on at the end. It's woven into the fabric of the learning objective throughout the meta policy learning phase. It guides the entire process towards stability and efficiency, even during adaptation. And the networks themselves are pretty standard but robust setups. The policy network uses RILU activations and hidden layers for learning complex patterns, and a 10 output to keep actions within reasonable bounds. Then you have Q networks, also MLPs, acting as critics to estimate the value of actions, guiding the policy improvement. It's a solid architecture for this kind of task.
Okay, this all sounds very elegant theoretically. Yeah. But does it actually work? This is where we look at the experiments, right? The proof is in the pudding, as they say. What kind of setups did they use? What robots? What environments?
They really put it through its paces. The experiments focus on motor learning and control using 3 standard, but challenging, agents in the Majoko physics simulator integrated with OpenAI Gym. These were the HalfCheetah, the Walker 2D, and the Hopper.
Ah, yeah, familiar benchmarks. Pretty complex, right?
Yeah, definitely. These are high-dimensional systems. The HalfCheetah, for instance, has 18 state dimensions, joint angles, velocities, body position, and 6 control dimensions for the joint torques. Controlling it effectively is non-trivial.
And how much training did they do? Was it thorough?
Oh, yeah. They ran 400 epochs of training with 1,000 environment steps per epoch. That's a lot of interaction. And critically, they used 10 different random seeds for each experiment.
Which is good practice, right? To make sure the results aren't just a fluke of initialization.
Exactly. It gives you statistical robustness. They also mentioned using NVIDIA A30 GPUs, so they clearly threw significant computational power at this.
Okay, serious testing. And how do they test the adaptability part? How do they simulate those perturbations or new tasks you mentioned earlier, like the crippled leg scenario?
They had a really clever and quite harsh set of out-of-distribution tasks and perturbations. For HalfCheetah, they varied its body mass, they changed the floor angle to simulate running uphill or downhill, and yes, they even crippled one leg, essentially paralyzing it.
Wow, okay.
For the Hopper, they paralyzed its thigh. And for the Walker 2D, a bipedal walker, they paralyzed its right thigh.
So they really force the agents to cope with significant unexpected changes to their bodies or environments. That sounds like a tough test for adaptation.
It absolutely is. It pushes the agent far beyond just memorizing movements for one specific scenario. It forces genuine adaptation.
So what did they measure? How did they evaluate performance beyond just, did it fall over?
They used a comprehensive set of metrics. First, the obvious one, average total reward. How well did it actually do the task over an episode?
Standard RL metric. Makes sense.
Second, they measured the average feedback norm, that Jacobian norm squared, B2. This tells you how sensitive the policy is to state changes. Lower is generally smoother, less reactive.
Okay, the don't overreact metric.
Right. Third, the average feed-forward norm, or jerk, AU2. This measures the smoothness of actions over time. Lower means less jerky movement.
The don't be jerky metric.
Exactly. And finally, average energy consumed calculated as the sum of squared control actions, U2. Basically, how much effort did the agent expend?
Right, efficiency. And they ran multiple episodes after training to get reliable numbers for these.
Yep, 10 full evaluation episodes per seed after training was completed. So, solid evaluation protocol.
Okay, drum roll time. How did the MBMPO plus minimum attention stack up against the others? Like standard MBMPO without the attention, or a good model-free baseline like soft actor critic, SAC?
The results are really quite compelling. Consistently better performance with minimum attention. Let's take HalfCheetah meta-training as an example. With minimum attention added, using a weight at 1.0, MBMPO achieved an average total reward of 900 and 721 nair on 9 of 128.
Okay, 900, 721. How did standard MBMPO do?
Standard MBMPO without the attention regularization only got 6,690 M7
Wow, that's a massive difference, over 3,000 points.
It's a huge jump. And look at the standard deviations, 128 for the attention version versus 318 for the standard. Much more consistent performance.
Way tighter. What about the model-free SAC?
SAC's final numbers weren't in the main tables for direct comparison in that specific setup, but the learning curves shown in the paper indicated it was significantly outperformed by the minimum attention approach, especially during the bulk of the training. The model-based approach with attention learned much faster and reached higher rewards.
Okay, so a clear win on reward and consistency. What about that variance reduction you mentioned earlier? Was the learning process itself smoother?
Absolutely. That was a critical finding. Visually clear from the learning curves. Minimum attention significantly reduced the variance during training. The learning curve was just smoother, less jagged, more predictable.
Which is great for reliability.
Hugely important. And it ties into the other metrics. The average feedback norm, remember, sensitivity to state, it was much lower for the minimum attention variant, 567 Nayimekis 53, compared to 783 Matanamini and Munson 35 for standard MBMPO.
So empirically, it was less reactive, less sensitive. It confirms the regularization is doing what it's supposed to.
Exactly. It's behaving in that calmer, smoother way.
And did that translate to energy savings? Was it actually more efficient?
It did, and this is really interesting from a practical standpoint. For HalfCheetah training, the normalized average energy consumed was 3.85, 0.05 with minimum attention.
Okay, and without it?
Standard MBMPO used 4.54 to 9ups.13.
So a noticeable drop in energy use.
Mm.
That's significant for real robots' battery life, wear and tear.
Absolutely. Less effort to achieve a better result. It suggests that smooth, non-reactive control is also inherently more efficient control.
Fascinating. Did they look at how things like the number of models in the ensemble affected performance, or how long those simulated trajectories should be?
They did. They ran hyperparameter sensitivity analyses. For the ensemble size, they found that more models generally helped, up to a point. Using 20 models gave the best results in their tests. More experts led to a better overall policy.
Okay, so bigger ensembles are generally good.
Right. But for the length of the simulated trajectories, how many steps they simulated inside the learned models, there was an optimal point. N128 steps worked best. If they went longer, like N256 or 512, performance actually started to decrease.
Huh. Why would simulating more steps hurt?
Probably because the learned models, even in an ensemble, aren't perfect. Simulating too far ahead might lead to an accumulation of prediction errors, introducing noise that harms the policy update. So there's a sweet spot, simulate enough to get good gradient information, but not so much that model errors dominate.
Interesting trade-off. Okay, let's talk about those heat maps. You mentioned the policy sensitivity analysis. What did they show visually?
The heat maps are really cool because they give you a qualitative feel for how the policy changes. They visualize the Jacobian norm, the sensitivity metric, across different state dimensions for the HalfCheetah. And the most striking visual difference is that the policy trained with minimum attention has much lower peak sensitivity, meaning it avoids those really extreme, sharp reactions. Even in situations where the state changes quite a bit, the control output doesn't suddenly spike as much as it might with the standard policy.
So it's genuinely less twitchy, more measured.
Exactly. The regularization directly penalizes those large derivatives, smoothing out the policy landscape. Now, both policies, the regularized one and the standard one, correctly identify similar regions where high sensitivity is needed. For example, the paper mentions low z-coordinate height combined with high forward velocity for HalfCheetah. That's a critical state for maintaining balance at speed, so you need some responsiveness there.
Right, you can't be completely insensitive.
Of course not. But the magnitude of the sensitivity in those critical regions is what changes. The standard policy might learn a very aggressive, highly reactive strategy there, leading to those really high peaks in the heat map.
Overcorrecting, maybe.
Potentially, yeah. Whereas the attention-based policy learns to handle that same critical situation, achieve the task, but with demonstrably lower control effort and reactivity. It finds a smoother, less expensive way to stay balanced.
So it's not just better numbers, it's actually learning a different, maybe more elegant control strategy.
That's exactly how I see it.
Ah,
It embodies this principle of achieving competence with minimal exertion, minimal reaction. It's a fundamentally different quality of control, more graceful, more efficient, inherently more stable.
we've spent a lot of time on HalfCheetah, which makes sense given the detail.
Mm.
But did these benefits carry over? Did minimum attention also help the Hopper and the Walker 2D, especially when they had those paralyzed legs? Was it consistently good?
Yes, and that's a really important point for showing the general applicability. The improvements were consistent across all the Mujoko agents they tested. Let's take the Hopper, for instance. Remember, it had a paralyzed thigh, a pretty major handicap.
Right.
The average total reward for MBMPO plus Manhattan during meta-training was 2,825 nanons, 1.25.
Okay, 2,825. And standard MB-MPO.
That was 2,475, deny 3.81. So again, a clear and significant improvement in performance even with the impairment. And look at that tiny standard deviation for the attention version, incredibly consistent.
Yeah, 1.25 is basically zero variance. What about the Walker?
Similar story for the Walker 2D, the bipedal robot, which had its right thigh paralyzed. The minimum attention approach pushed the total reward during training up to 338 denies, Menarun 48,
Compared to
2,399 by 9-1's Mattes 594 for standard MBMPO.
wow, another big jump in reward. And look at that huge reduction in variance again from this 940 down to 148. That's massive stabilization.
It really is. It shows the walker learned a much more robust and functional walking gait despite the damage, and the learning process itself was far more reliable. And like you said, these aren't just single numbers. The paper includes detailed tables in the appendix showing performance at different stages, early, middle, final, for both training and testing across all agents. And that data consistently confirms the story. Minimum attention robustly boosts performance, stabilizes learning, and improves adaptation, even when the agents face significant structural damage or environmental shifts like those changing floor angles.
So it really does seem to be a general principle, not just something that happened to work well on the HalfCheetah.
The evidence strongly suggests that, yes, it's a robust enhancement.
That's really cool. It's amazing how this principle of encouraging smoother, less reactive control ends up making the policies more robust and generalizable overall. It feels like it's building agents that aren't just good at their task, but good at it gracefully and efficiently, even when things go wrong, kind of like building in resilience.
I think that's a great way to put it. The paper talks about aiming for policies that are safer or less biased by avoiding extreme actions. And it seems that by doing so, they paradoxically become more effective and adaptable when faced with the unexpected.
Less is more, in a sense.
In a sense, yeah. Less reactive effort leads to greater overall competence and robustness. It's a key insight for building AI we can actually trust in the real world.
Okay, so this seems like a really solid step forward for making RL agents more robust, more adaptable. What do the researchers see as the bigger picture? Where might this minimum attention idea go next? What are the broader implications?
They definitely hint at some interesting future directions. One idea is exploring its use in algorithmic debiasing.
Debiasing. How does smoothness relate to bias?
Well, the thinking might be that if an agent's actions are inherently less extreme, less prone to wild swings based on small input changes, maybe its resulting strategies will also be less prone to exhibiting unwanted biases learned from the data or environment. It encourages more moderate responses, potentially leading to fairer or more balanced behavior across different situations.
That's an intriguing thought. A bit speculative, maybe, but interesting.
It is. Another related area they mention is multitask learning. The inherent smoothness and efficiency might help agents generalize better across a wider range of related tasks, rather than learning highly specialized, brittle policies for each one.
Right, because the underlying control philosophy is more general.
Perhaps, yeah. It promotes a more fundamental kind of competence.
And what about that really fascinating, maybe slightly out there idea about large language models? Could minimum attention apply there?
Yeah, that was a provocative point in the paper. They posed the question, Could minimum attention help degenerate singularities or rare events in LLMs?
Okay, what does that mean in plain English?
Well, LLMs sometimes produce weird, nonsensical outputs, singularities, or behave unpredictably rare events like generating harmful content or just going completely off topic. It's a stability issue in a very complex system.
Right.
The speculation is whether a principle designed to smooth out and stabilize the dynamics of physical systems, like robots, could somehow be adapted to stabilize the internal dynamics or output generation of these massive language models.
That's a big leap, from robot joints to word probabilities.
It is, but it points to a potentially deep connection. Maybe penalizing abrupt changes in the model's internal states or output distributions could lead to more coherent, stable, and predictable language generation. It's definitely food for thought. Could control theory principles help tame the unpredictability of LLMs? Very interesting research question.
Absolutely. Now, no research is perfect. What did the authors see as the main limitations or the necessary next steps for this work?
The main one they highlighted is that their validation was primarily within model-based RL, specifically using their MB-MPO framework.
Okay.
So a crucial next step is to explore how well minimum attention works in model-free RL. Model-free methods are still dominant in many areas, especially for really complex tasks where learning an accurate model is just too hard.
Right, so can you get similar benefits without having that explicit model to regularize?
Exactly. How would you even apply the penalty? On the policy directly, on learned features. That needs investigation. It's key for broader adoption. They also mentioned the general limitations of gradient-based meta-learning, like MAMML. It works well, but it can be complex, computationally expensive, and might struggle with very diverse task distributions.
So could minimum attention be integrated with other meta-learning approaches?
That's another avenue, exploring it within different multitask learning frameworks, or maybe even gradient-free meta-learning methods, could potentially overcome some of MAML's limitations and broaden its applicability further.
Makes sense. Anything else?
One more point, which is crucial for really solidifying this concept in the field, the need for deeper theoretic analysis.
More math.
More rigorous math, yeah. While the empirical results are strong, having formal proofs about the stability and boundedness guarantees provided by minimum attention would be invaluable. They suggest using tools from control theory, like Lyapunov potentials. Essentially, can we mathematically prove that adding this regularization always leads to a more stable system under certain conditions?
Like a formal safety certificate.
Kind of, yeah. It would provide strong theoretical backing for the empirical success and build more confidence for using it in critical applications. It would move it from "it seems to work really well" to "we know precisely why and when it guarantees stability."
Okay, so wrapping things up, what's the big takeaway for our listeners? Whether they're deep in AI research or just trying to keep up, what does minimum attention really mean for the future?
And I think the core message is that how an agent learns and controls itself matters just as much as the final performance. Minimum attention offers a pathway to agents that learn faster, adapt better, and operate more stably and efficiently, especially when things get messy and unpredictable. It shows that borrowing elegant ideas from nature and fundamental physics, like this least action principle, can lead to genuinely more robust and, frankly, more intelligent-seeming AI systems. Systems that handle the real world more gracefully.
Yeah, this deep dive really highlights how focusing on control, quality, smoothness, responsiveness, efficiency isn't just about aesthetics. It directly translates to better performance and robustness in complex tasks, like robotics. It feels like important groundwork for more resilient AI down the road.
Absolutely. As we build AI systems that interact more closely with our physical world, self-driving cars, helper robots, drones, this ability to control them with, let's say, intelligent restraint becomes paramount.
Intelligent restraint, I like that.
Think about it. A self-driving car that reacts smoothly to a sudden obstacle, not swerving violently. A rescue robot that navigates rubble carefully and efficiently, not erratically. Minimum attention points towards achieving that kind of competence. The fundamental insight seems to be that sometimes less extreme attention, less reactive effort, actually leads to greater overall capability and safety. It's about smarter control, not just stronger control.
A really powerful idea. Well, that's all the time we have for this deep dive into the fascinating world of meta-reinforcement learning with minimum attention. Thanks for joining us. Until next time, keep exploring, keep learning, and keep asking those deep questions.